Welcome everyone to the second part of the quantitative thinking component of the study design and quantitative thinking module. So, in this second part, we will continue with where we left off from the first part. In the first part, we looked at why we use statistical methods and we started discussing key statistical quantities commonly used. We ended with talking about a very important quantity, namely the confidence interval. The next important component of a statistical analysis is statistical hypothesis testing. You would have all heard of this term, statistical hypothesis testing, setting up nulls, alternate, p-values. Let's spend 5 minutes discussing what this means and how it is carried out. Let's take an example. So, the image that you see here is of the peninsular rock lizard, and in this species the males in orange and black are larger than females, more conspicuously colored than females. They compete for territories and also for females. So, imagine that I am an ecologist interested in male-male competition strategies in this lizard species. And because competition is costly, you can make yourself conspicuous to predators, you spend energy displaying, if you fight you can get injured or even die. My hypothesis is that males compete strategically and invest more in competition and aggressive behavior under high competitor threat situations and less under low competitor threat. So, the question I am interested in is, do males adjust costly aggressive behavior to the level of threat that the competitor poses, and my prediction is that aggressive behavior will increase with the level of threat. To address this question, I carry out a study in which I experimentally simulate low and high threat levels using these 3D printed models like the one shown to you in the figure here. This is a 3D printed model and this is a resident male lizard. So, I use 3D printed models and simulate low threat by simulating an intrusion into a peripheral part of the territory, and high threat whereas simulate an intrusion into a central part of the territory. Now, let us say these are the data that I have got. This is just an example of the kind of data that one might get. So, I have measured aggressive behavior on a sample of males exposed to low threat and aggressive behaviors for a sample of males exposed to high threat. So, my question here is the aggressive behavior under high threat higher as predicted than aggressive behavior at low threat? So, we use statistical hypothesis testing to ask whether there is a difference between these two categories of threat level or not. What we seek to understand is whether there is a true difference in population parameters for low and high threat. So, for example, is the mean aggressive behavior of males under low threat, is the true population mean different from the mean difference, the mean aggressive behavior under high threat? Is this the true situation in my population, or do males show the same aggressive behavior whether they experience low threat or high threat? So, do we have the same population parameter for both low and high threat? So, this is what I seek to contrast when I carry out statistical hypothesis testing. So, how does statistical hypothesis testing work? We first establish the null distribution. So, the null hypothesis is typically a hypothesis of no effect. That is, we say mean 1 equals mean 2. The mean aggressive behavior of males under low threat equals the mean aggressive behavior of males under high threat. And the actual value that we get, the mean difference that we get, is what we expect by chance alone. That is, here is the distribution of mean differences between low and high threat situations under the null of no difference. So, even though no difference would mean a value of 0, we will never get aggressive behaviors that are exactly the same from two samples. So, occasionally we will get one sample mean being higher than the other. So, sometimes low threat mean might be higher than the high threat mean, and sometimes the high threat mean might be higher than the low threat mean. So, this shows you the distribution of the difference under the null of no effect, no distribution. So, you can see most of the time the probability is highest for values that are close to 0, but occasionally you can get large differences between low and high threat situations. That is the tail, that is what the tail of this distribution represents. So, what we then do as the next step, we compare our observed difference, our observed statistic with the null distribution and calculate the p-value. That is, if we observe a certain value, say 1.2 or some particular value, what is the probability of getting that value or something more extreme under the null that there is no difference between the means? So, let us take two examples. So, suppose I get a standardized difference of 1.05. So, 1.05 lies somewhere here, and we usually calculate a two-tailed p-value. That is, we say what is the probability of getting 1.05 or something more extreme, either more negative or more positive under the null that there is no difference between the two means. In this case, if you sum up the probability under the two tails more extreme than 1.05, you get a value of 0.3. What this tells you is that values like 1.05 or more extreme are actually quite likely under a null of no effect. So, we cannot reject the null. The null actually might produce a value like 1.054. So, we fail to reject the null and we conclude, we make the inference that there is no real difference for a detectable difference between low and high threat situations. On the other hand, if we get a value like 3.38 now, what is the probability of getting 3.38 or something even more extreme under the null? And again we consider both tails of the distribution. So, 3.38 and more extreme or minus 3.38 and more extreme. And here, as you can see, the probability of getting such values is very small, p equals 0.002. So, then we say okay, the null distribution does not really represent a value like 3.38 very well, because a value like 3.38 is not, values like that are not very likely under the null. Therefore, we reject the null and say here we have evidence for a detectable difference between low and high threat situations. Now, it is very important to realize that the statistical null hypothesis testing approach has to be used with caution. We cannot blindly follow it. Several mistakes can be made. Here are the two most common mistakes. First, we can wrongly reject the null and conclude that there is an ecological pattern even when there is not. So, remember, even under the null of no difference, occasionally you can get very large values. There is a small probability associated with getting such large values. Usually we keep that cutoff at 5%. That is, we say, okay, we will consider values in the 5% extremes of both tails put together as values that are very unlikely, but occasionally we can get such values even when there is no difference. So, there is a 5% chance, if we use such a cutoff, there is a 5% chance of wrongly rejecting a true null. This is often called type 1 error. The second mistake that we can make is, even when there is a true ecological effect, if there is truly a difference between low and high threat in aggressive behavior, we may miss out on finding it. So, take this situation here. Suppose there is a true difference in aggressive behavior of say around 3.5, and we are contrasting it against a null distribution of 0. So, now if our sampling distribution is quite narrow, maybe because we have large sample sizes, there is not much variation in the population. So, we are able to estimate, come up with our estimate quite precisely. Then in a situation like this, we will correctly reject the null and detect an effect. On the other hand, suppose this is our sampling distribution. So, still there is a true difference of 3.5, and here you have the null. However, maybe we have a wide sampling distribution, maybe because our sample sizes are low and we are not able to capture the variation in the population very well. We have very wide sampling distribution. So, in a case like this, even though there is a true ecological pattern out there, a true difference between low and high threat situations, we will not be able to detect it. We will not reject the null distribution. We will fail to reject the null and we will wrongly conclude that there is no effect even when there is one. Related to this, another point to remember is that statistical significance may not mean biological significance. So, rather than just use p values and cutoffs like 0.05 and say something interesting is going on if p is less than 0.05 and there is no effect if p is greater than 0.05, it is very important to look at the actual effect sizes. Remember from the previous video that the effect size refers to how much of a difference there is, not just is there a difference or not. And confidence interval, what is the plausible range that this difference is likely to take? How close is our sample mean to the true population mean? Rely on effect sizes and confidence intervals rather than p values. Let me explain this to you with an example. So, let us go back to an example we have talked about before, which is the impact of roads on butterfly habitat use. So, imagine that I am estimating the difference in habitat use from far away from the road, in plots far away from the road compared to plots near the road. So, what this shows you here is butterfly habitat use in terms of relative abundance in plots far away minus near. So, a value of 0 here would mean no difference, negative value would mean greater habitat use near the road, positive values mean greater habitat use far from the road. And I have shown you two situations here. These two situations, if you carry out a null statistical hypothesis test with the null that there is no difference, far minus near equals 0, here you will get p greater than 0.05. These are the estimates and the bars are 95% confidence intervals. And I have shown you two situations here where p is less than 0.05. So, we reject the null of no difference and conclude that there is evidence for a difference. Again here too, these are the estimates in squares and the bars are 95% confidence intervals, which tell you what is the range of values within which that population parameter is likely to fall with a 95% probability. So, based on these data, two situations are very clear. Take this situation here, here you have a large effect size, the difference in habitat use in relative abundance of butterflies is almost 30 on average, and the confidence interval also indicates that the effect size is quite large. It is from 18 to 20 difference individuals per plot to 40 individuals per plot. So, quite a large difference in habitat use. P value is also less than 0.05. Take this situation here, p value is greater than 0.05, saying we cannot reject the null. We have to conclude that there really is no difference between far and near plots, and the confidence interval is also narrow, very precise, and it only includes very small differences, positive or negative. So, here again we can make a very confident conclusion that there is probably not much of a difference in habitat use between far and near plots. However, the other two situations are not so clear. Take this situation here, the p value less than 0.05 would make us conclude that yes, there is a statistical significant difference between far and near plots. So, yes, roads impact butterflies. However, look at the effect size, it is very small and it is in fact not very different from the case where we conclude that there is no effect. So, there is a very small effect size and the confidence interval also suggests that the small effect size has been precisely estimated. So, in fact, here even though this is a statistically significant result, biologically, ecologically it may not mean much at all. Roads may not impact butterflies very much. Take this other situation, here p greater than 0.05, which means we fail to reject the null and the confidence interval including 0 reinforces that. 0 is part of the confidence interval, no difference is part of the 95% confidence interval. So, do we then conclude that there is no difference between plots far and near? Well, the effect size is quite large and the confidence interval suggests that large effect sizes are as much a part of it as small effect sizes. So, in fact, this is a situation where even though the null hypothesis test tells you that you should infer there is no difference, the effect size and confidence interval tells you that we have a lot of uncertainty here, and in fact, we might have a large effect size and suggests that this is a case which would need to be probed further. Okay. Let us move on to the next point, which is about choosing the statistical analysis. Now, how do we figure out what kind of a statistical model we need? Let me explain this to you with a couple of examples, and the motivation here is not to describe to you specific statistical models like regression, generalized linear model and so on, but to give you a feel for the logic. How do we go about? What are the steps involved in figuring out the analysis that we need? So, let us take this example. Suppose I am interested in the impact of disturbance on invasive plant growth. There is a very popular hypothesis that invasive plants can benefit from anthropogenic disturbance and growth is in fact enhanced by disturbance. What I strongly recommend is to have a very organized approach towards figuring out your statistical analysis. So, here is what I have found very useful. The first step is to be very clear what is the ecological question that you want your analysis to answer. In this case, it would be, I would like to figure out the relationship between invasive plant growth and disturbance. The second step is to be clear what is the form of the relationship that I want to estimate. So, this is often called the deterministic part of the model. On average, how do I expect y to be related to x? Let us say I have a very simple expectation. I expect a straight line relationship. As disturbance increases, I expect invasive plant growth to increase linearly. So, I then find a suitable function. So, here I will use it is very simple, I use the equation for a straight line. However, based on theory or based on previous work, I might want to choose a different function to fit to the data. So, this step here is about figuring out the shape of the relationship, what kind of a function do you want to fit to your data. The third step is to then think about what is the nature of variation in the data. How will data points deviate from the deterministic part? So, on average we expect a straight line relationship, but of course data will deviate from that. So, what is the nature of variation in the data? This is called the stochastic part of the statistical model. So, in this case I might expect that growth, suppose I measure growth as change in the girth of the plant per unit time, it might be reasonable to expect growth to be a continuous variable that is normally distributed. Once I figure out the deterministic and the stochastic part of the model, that helps me choose the statistical model. So, in this case if I want to fit a straight line and I can assume normal distribution, the most common model that will first come to mind is a linear regression. So, I fit a linear regression to the data. The next step is to check the assumptions. Are the assumptions for a linear regression, are they satisfied? Then I find estimates and confidence interval. In this case it would be finding the intercept and the slope and the confidence intervals around the intercept and the slope. I might also want to carry out statistical hypothesis tests. The last step is to now use these statistical results from fitting these statistical models to make conclusions or inference about the question. So, depending on the magnitude of the slope, for every sensible change in disturbance, by how much does invasive plant growth increase? If this is fairly large and has been estimated precisely, I might then conclude that there is a certain amount of relationship between invasive plant growth and disturbance. On the other hand, if the slope is close to 0 or negligible, then I might conclude that actually disturbance does not seem to influence invasive plant growth. Let us take another example. Suppose I am interested in how species richness of a group of insects. How is species richness related to the area of a habitat patch, and not just that, but to the matrix around the habitat patch, because the matrix can influence how well species can individuals can move in and out of the habitat patch. It can influence functional connectivity between habitat patches. So, let us again go through the steps in statistical analysis. First, what is the question that this analysis specifically aims to answer? So, here I am interested in the relationship between species richness and patch size on the one hand and matrix type on the other. Second point, what form of the relationship is to be estimated? What is the deterministic part of the model? So, say drawing from theory, I might expect that species richness is a power function, follows a power function of area. So, I have illustrated that to you. So, the relationship between species richness and area of the habitat patch, I expect is some form of a power function and I need to estimate the power. I also expect a difference between matrix types. So, I expect a matrix that allows for better movement, for better connectivity. I expect species richness to increase much more rapidly than for the same area, a matrix that is not so connective, that is much more resistant to species movement in and out of the habitat patch. You should see fewer species in a habitat patch of the same area, but with a more resistant matrix type around it compared to a more permeable matrix type around it. The third step is to think of the stochastic part of the model. What is the nature of variation in the data? Here species richness is a count. We have number of species in a particular habitat patch. So, then a suitable distribution that we can think of to capture this variation in the data is a Poisson distribution. So, given the deterministic part and the stochastic part that I have described to you here, the first kind of model that this will point to is a generalized linear model or a GLM with Poisson error structure. Now, here the important thing is not for you to know what a linear regression is, how it works, or what a GLM is and how it works. What I want to tell you is that if you are able to articulate your question clearly, if you are able to articulate the type of relationship you want to fit and the kind of function, kind of shape which will determine the kind of function you want to fit, and the nature, if you understand the nature of variation in the data, that will facilitate finding out the appropriate statistical model to use. And either you can learn about these different statistical models or you can approach ecologists and statisticians to help you figure out once you have these 3 steps clear in your mind. The next step after that is of course to fit the GLM, check the assumptions, whether the assumptions of the GLM are met, find the estimates and confidence intervals, maybe carry out statistical hypothesis tests. And the last step is to take the results from the statistical analysis and make conclusions about your question. So, what is the value of the power and how well have you estimated the coefficients in this function? How well have you estimated the difference between the matrix types? How much confidence do you have in that estimated difference? These will let you make inferences about the relationship between species richness and patch size and matrix type, and lets you address the original question, the hypotheses that you started with. Finally, let us end by talking about 2 common mistakes that are often made when carrying out statistical analyses, and the reason I want to talk to you about these 2 mistakes is because we have a replicability crisis in science. Researchers have pointed out that a lot of studies may not actually be reliable. That is, we may not be able to actually have much confidence in the conclusions from those studies, and there are 2 reasons to do with how statistical analyses are carried out that contribute towards this lack of confidence in the results from studies. So, the first common mistake is p hacking or data dredging. What does p hacking or data dredging mean? P hacking refers to where we explore and test lots of relationships. So, suppose I am interested in looking at the species richness of this insect taxa in a landscape, and I look at the effect of patch size, I look at the effect of distance between patches, I look at matrix type, I look at seasonal patterns, I look at the effect of human disturbance, different kinds of human disturbance. So, there are a lot of variables and I try out different combinations of these variables, I try out different shapes, straight line, different non-linear relationships. The problem with exploring and testing lots of relationships is that suppose you do find a relationship between species richness and one of these variables. If I were to carry out this study again, that relationship may disappear. Now you can see here you have a much lower slope and much less of the variation is explained, the correlation is much less. If you were to calculate r square, which is the amount of variation explained by a model, the r squared here would be much lower than the r squared variation explained by model, the r square here. What this indicates is that noise in the sample has been mistaken for signal. So, whenever you test for a lot of relationships, you will find something just by chance, and you will find a relationship that is not a general property of your population, but some peculiarity of your sample. P hacking or data dredging refers to this problem. The second common mistake is to focus on p values rather than effect sizes and confidence intervals, and this becomes much bigger a problem with big data. So, when you have a very large data set, you can pick up small, negligible, biologically insignificant effects. So, you will get a p value that is very tiny, but if you look at the amount of variation explained or the effect size, you will find that it is small. In this example case, the p value is extremely tiny, suggesting very high statistical significance, but there is absolutely low biological significance. R square is very small, only 3% of the variation in the data is explained, and the slope is negligible. So, for a unit change in x, there is a very small change in y, suggesting that this is not very important biologically. If we focus on effect sizes and confidence intervals, we would correctly conclude that here you have statistical significance, but this may not be significant ecologically. So, what are the solutions to these common mistakes? First, formulate statistical analysis based on the ecological hypotheses and quantify only these specified relationships that are related, that you are predicting based on your ecological hypotheses. So, try to avoid data dredging. If you are carrying out an exploratory study where you do not have very clear hypotheses, then it is fine, but declare that you are really exploring patterns and then propose that the relationship you find could be interesting and go out and then test it rigorously. Focus on biological significance. How large is the effect? How precisely have I been able to estimate it, and not on p values, not on statistical significance. And for all this, good study design is crucial. Statistics cannot rescue from bad study design and bad data. So, with that, we end the second part of the quantitative thinking component of this module, where we have gone over why we use statistical methods, what are key quantities, how do we decide what kind of a model or method to use, and what are some common mistakes that can lead to wrong results. With that, this module on study design and quantitative thinking ends here. Thank you.